All right, so something like this is going to be useful that we can do this in the near future. Near meaning maybe tomorrow. But what we're saying here is that they're telling you these two triangles are congruent. And if we look over here, the congruence occurs because of side, 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 right? And if they're congruent by side, 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 we should be able to recognize that there are corresponding parts that are also congruent. And if I look at, they want me to find DF. So I look at DF in the name, and that should match up to, over here, A and C, right? So DF in AC, those should be congruent segments. And again, you can kind of verify that through the picture because the picture has 3 marks in both those, right? Now, those two segments, one of them, AC, has an expression 3x plus 34, and DF has an expression 5x plus 2. And my hope is that we understand that when we see an expression like that, that is representing some unknown number, right? When you know what x is, you then know a concrete numerical value for AC. The logic is that that concrete numerical value should be the exact same thing for DF. All right, and that equation, relating those two expressions to one another, will allow you to figure out what that x value is that provides that concrete value for AC and DF. So we set that equation up. I'm going to subtract 3x from both sides and subtract 2 from both sides. So then it gives me x to be 16. Okay? I've seen a lot of people just type in 16 here, and it's wrong. Okay? Because what are they asking me for? DF. They don't ask me for x. And that's something that you got to kind of break your mind from, because I knew in Algebra 1, we kind of train you to do that, right? Solve for x every single time. And then you get here, and so you got to do a little bit more with that x. So they want to know DF. So I'm going to come over to DF, and I'll plug 16 in for that x. So it'd be 5 times 16 plus 2. So 5 times 16 is 80, plus 2 would be 82, right? All right. Before I type 82 into that box, I'm going to go over to AC, and what should I, if I evaluate AC's expression with x being 16, what should I get back? I should get 82, and that's kind of the built-in check to make sure that my value is right. So I'm going to take in 3 times 16 plus then 34, okay? Well, 3 16s is 48. So 48 plus 34, add those together, I get the same 82, right? So that's verification. It's a quick check to be certain that that is the right answer for that question, okay? Other questions, I think 23 does this, or 24. They really start you off with the same information. Say that these two triangles are congruent, but then they want you to find y. Okay? Well, I look over my pictures, and maybe the first one I look at, I'm going to find where y is. Y is in angle B, right? So now I come over to angle B in the name, and that's going to correspond to, it's the middle letter, so it's got to correspond to angle E here, right? And then I can say 90 plus y is equal to, come the E in the picture, and its expression is 5y minus 30. And now I have the ability to find y and maybe those angle measurements. Okay, just doing that real quick for you, you'd get 4y, 120, y would be 30. You can plug that in. 5y minus 30, that would be what, 120? And then this would be 120 as well. So, other questions like 23, 24, I think 21 is another one where they ask you to do distances or something like that. The one thing I want to show you with 21, came from a different textbook, very similar, but you see there's options A, B, and C. Everybody's going to have option A in that question. B and C are the idea that what happens if we set equations up and we don't get a solution back from them, or we get something that doesn't make a whole lot of sense. For instance, let's say, in everybody's question, these two things really never come into play. Okay? So you'll always go into A, choose A, and then plug in your number for X in those braces. Those braces, and I don't know if you guys talk about this now, number one, that's notation. It's called a set. Okay, you see there a set, and a set algebraically, and there's a whole branch of mathematics that deals with just sets. Okay, it's called set theory. But it's just a collection of things. Okay, whatever you want them to be. Okay, you want them to be collections of names, collections of a lot of times we talk about cards. Okay, playing cards like ace, jack, king, queen, that kind of stuff. A collection of things could be flavors of ice cream. Doesn't really matter. Those are sets. Okay, mathematically speaking, we like sets to be numbers. Okay. When you have solutions to any equation, okay, your solutions, algebraically, we denote them. Instead of saying, you guys are let's just do this problem real quick. You guys are familiar with, setting your equations up, solving, saying x is equal to whatever, right? Okay. So let's go ahead and do this one. Hopefully we recognize that AC and DF would be equal to one another, right? Okay, by the CPCTC statement. So I'm going to say 4x plus 38 should equal 6x plus 8. I'll subtract 4x from both sides, so I get 2x over here, I get 30 over here, x will be 15, right? Okay, and you guys are probably most comfortable writing x equals 15. Okay, an alternative way of doing that is to put curly braces and then 15, and that is saying the exact same thing. Okay, but now we know that this problem has one and only one solution. Okay, sometimes you would write it this way: x such that x equals 15. But those curly braces tell you you have a set of solutions, and your set could be one thing. Your set could actually be an infinite number of things. Okay, let's think about how this question can be altered to where you get infinite number of solutions. Let's say that instead of that being 6x plus 8, let's say it was 4x plus 38. Okay, so I take AC and compare it to DF. I create an equation, 4x plus 38 equals 4x plus 38. Okay? You can stop there because the left-hand side is what compared to the right? Exactly the same, right? So choose an x value, plug it in on the left. Plug in 0. What do you get? 38. Plug in on the right. What do you get? 38. Is 38 equal to 38? Yeah. Plug in 1. You get 42 here, right? You get 42 there, right? Is 42 equal to 42? So no matter what you plug in for x, you're going to get what we refer to as a true statement. Some number equal to itself. Okay? If you go through and try to solve this, you don't recognize that to the same. And sometimes you might not. Go through and solve this. Many people say, I'm going to subtract 4x from both sides. I get an equation where maybe I don't know what to do with that statement. Okay? And really, you don't do anything. You just make a qualitative statement, a qualitative argument that says, I know that that's a true statement. And when I get a true statement, algebraically, it kind of tells me that my solutions are infinite. X can be anything. Does that kind of make sense? Now, for us, we would actually, because that x is attached to a picture and a length, we would actually have to do maybe a little bit more to say, x cannot be negative 10. If x is negative 10, I get a distance of negative 2 there, right? And distance can't be negative. So we have to do a little bit more work. We'll talk about that later in the year. But if you ever do work, you set up an equation, and you get down to a point where it just gives you a number is equal to number, try to determine, is that true or is that false? If it's true, you ultimately get infinite solutions, and that's what this option here, B, is saying. Okay? X such that x is a real number, basically meaning any number off the number line. Okay? Obviously, we're not choosing that. That's not the right answer. Another way, okay, kind of addressing what C would look like. Let's say that this equation was 4x plus 10. Okay, so I set up my equation, 4x plus 38 equals 4x plus 10. Again, they are different, so maybe I go through and I start solving. I subtract 4x from both sides. I get 38 is equal to 10, right? What kind of statement is that? Is that true or is that false? That's false. Okay? So when you come up with a false concept, that basically tells you x cannot be anything. There are no solutions. Okay? There are no solutions. And the way we showed no solutions as a set is we use that little circle with that slash through. Okay? And it just says no solutions. Okay? You've seen this before. You have done this in Algebra 1. Okay? You might not have remembered doing this, but it was with systems of equations. Mrs. Coles introduced, or Mr. Herr, Mr. McCoy, whoever you had, would have talked about what we call inconsistent and consistent systems of equations. Okay? And it kind of talks about how many solutions you get. Do you guys understand? You know that whenever you have an equation, the left-hand side of your equation is a graph, and the right-hand side of your equation is a graph? So let's say that I take the problem that we were doing. Let me pull that back up. We had 4x plus 38 is equal to 6x plus 8, right? So I'm going to let the left-hand side be a line. Okay, so it's 4x plus 38. So I'm going to go type in, just to get at the graph, and I got to introduce y, but y equals 4x plus 38. Okay? Then I'm going to type in 6x plus 8, and that has to be y equals 6x plus 8. Okay? Now I'm going to zoom out a little bit, but we eventually see that those are two lines, right? Those two lines are going to intersect right there, correct? Okay. Now I'm going to ask it for the intersection, and this is what you guys did with systems last year. Okay. So if we set up a system equation, use elimination or substitution, we would find this information. But if I click on the intersection of those two, it gives me that A point. But look over here. The 15 that we found algebraically by solving that equation is always the x value of where those two lines cross graphically. Does that make sense, everyone? Okay. So let me show you something that you talked about last year. Let's say that I had, let's go back to the idea that we had maybe an equation that looked like 4x plus 38, okay, and then one that was 4x plus 10. We subtract 4x from both sides. Where did it go? Come on. Equals y. It froze. There we go. Yeah, it's g of x, doesn't matter. I'll put y in there. All right. If we were to solve 4x plus 38 equals 4x plus 10, that gave us 38 equals 10, right? Which was a false statement. And you see why that's a false statement graphically. What are those lines? Where'd they go? Sorry. Don't know why they deleted. All right. What are those lines compared to one another? Parallel. So will they ever intersect and provide me that point? No. Okay. But what happens if I do this? Okay. Let's say that I have, it's kind of silly maybe to look at it as 4x plus 38 and then another graph of 4x plus 38. But what did that do? Put the two lines on top of one another, right? Sometimes you would have seen it like this probably last year algebraically. Instead of two identical graphs or equations, you were sending like 2y equals 8x plus then maybe, what's 38 times 2? 76? And it provides, when I graph it, the exact same line, right? Does that make sense to everybody? Okay. So how many times do those, even though those are two lines, you were seeing over here, they're graphing two lines, and if I maybe make one a lot fatter, make this one a little bit fatter, but change its color. Okay, let's do it this way. Let's make that one the fat one. And make this one the skinny one. Is that going to work? All right, you see, you can't see it in front of you, but I can see it pretty easily. You can kind of see the black one on top of the red one, right? Does that make sense, everybody? So how many times do those two lines intersect? An infinite number of times, okay? And that would have been provided algebraically with a statement like 38 equals 38, or 0 equals 0, 5 equals 5, whatever, okay? So that being said, I think it's important to talk about and understand the logic behind that question, how these solutions be presented to you. But again, for everybody, those two were not options. But I did want to talk about what that meant to you. Okay, that is something that's important as you go through the rest of your high school and being able to recognize what sets are and that kind of stuff. We do that a lot in college algebra.